Welcome to the 10th in our series of videos having a look at GAGE. This particular one we're going to explore the notions of steering behaviours and a little bit about collision detection and collision response. We'll start off with steering first of all. Now actually for both of these, as it's true for most of these topics, they're large complex topics in their own right, so as always we're going to be scratching the surface of them, but hopefully doing enough that we can get some useful functional behaviour from them. But we'll start off first of all with steering behaviours. And steering behaviours, you can view it as part of the broad AI area, where you want to give your game entity some ability, algorithms that help them navigate and move through the world that they're in. And there can be lots of different ways you can do this. So in terms of the screenshot you can see here, you can imagine these different characters. They may be moving around within their particular world. In some cases they'll have a specific target location that they'll need to plan out a route that you get to. It's known as pathfinding. In other cases there may just be sort of a bunch of things that they're doing that they don't want to approach something too quickly. They may want to chase after something else. They may want to sort of head in a rough direction, but to avoid bumping into things. So the ability to give game objects movement capability, so they can move around within their environment in an appropriate way, is what we mean by steering behaviours, or that's a subset of it. Lots of different aspects to it. So this one here, the screenshot here covers the idea you can have individual characters that are moving around, avoiding objects. You can get more sophisticated, and lots of games do get more sophisticated. So if it's your typical RTS, so here it may be that the player is selecting a whole bunch of objects and giving them an individual command. So then you're looking at how these things not deal with things individually, but either move in certain formations or move alongside a number of other entities where they want to somehow combine or sequence their behaviour. So you can get a lot of quite interesting aspects come out of it. So there's convergence on a certain point, but you want to make sure all of the entities, whilst trying to do that, don't move into one another sort of area. And importantly, it just doesn't, or thinking about steering algorithms, it just doesn't hold simply for your traditional game objects. So here you have sort of a picture of Hearthstone. And there's lots of different interactions here where things move about. Now, it could be there's a particular special effect where you want to have a number of, in this case, sort of the particles go out that home in a certain target location. That's a particle effect. It could be that whenever you add an entity down onto the play area, you want to shuffle the things across to make space for it. That's again a movement-based one, steering behaviour. It could be that whenever you're playing a new card or shuffling through the cards that are available, you want them to move in certain ways. So the steering algorithms, the ones that give game entities an opportunity to move in certain ways, they're actually quite flexible in terms of what they can be applied to. So I'll show you a very simple demo of one of the activities we're looking at, and again you can find a number of these online, but this one here, there's a number of entities. Wherever I click on the screen is where they try to go to. So the minute they're all trying to go into the corner, I could click down here just behind the lower grey rectangle, and that'll get all of these ones then to head over. So they're chasing after the particular location. The other spheres, they get pushed out of the way, but they're also being dragged back into their original location. So that's an illustration of where you have steering behaviours, where you can give things in individual control. Each of them try to do it, but there can be constraints in the way, for example, the other entities. And if you look back over at the sort of upper left-hand side of the circle, you can see actually that the two entities haven't been able to get back precisely the way they were. And that's going to be one of the characteristics of steering behaviours. You can give a bunch of intentions, and entities will try to use them as best they can, but often it's a balancing act depending upon what other competing elements you have in the environment. We'll have a look now at some of the code just to see what it does. And we'll run this first of all so you get a bit of a feel as to the steering behaviours we're talking about inside the GAGE framework. It's inside the spaceship demo. So if we're in here, we've got a couple of things. Now I can move my ship across the screen, and let's see, I'll find, if I can find a turret. So there's two styles of behaviors here. So one, we have the green AI controlled spaceships. They are trying to follow the red player ship. So they'll always head towards the player ship, but in doing so, they're also trying to avoid colliding with themselves, colliding with the turrets, colliding with the asteroids. So they're trying to keep apart from one another whilst chasing after the player. The turrets, they don't change their absolute position, but they do rotate, and they will try to rotate so that they're always looking towards the player in terms of the red spaceship. So these are illustrations here of different steering behaviors where we've gone to our entities and we're using either a look at, want you to look at a certain thing, or we're using a seek, we're going you to go to a certain thing, or separate to stay apart from other ones, and combining these together to give that overall control and overall behavior. So we can have a look at some of the code then that actually does this. In terms of the relevant class, so inside our GAGE, inside our utils, we have a steering behaviors Java file. So it's part of the util class overall. And inside this one here, it contains the different algorithms that we have available. Now, for steering, there's lots of different types of algorithm, and if you get a good book on Game AI, you'll be able to see all of these different ones. The steering behaviors implements a number of them, not the majority, just a number of common ones. So there's other types of steering behavior that are available, and quite often things get interesting in terms of steering behavior when you're trying to combine together several different behaviors. That I want you to try to chase after something whilst avoiding other obstacles. So how you actually combine them together, the different individual behaviors, is where it does get more interesting. And I'll show you one example when we're having a look at the Seeker spaceship, because they do have to balance a couple of different potentially competing drives. But we'll go through our steering behaviors first of all. So it's a utility one. It basically contains a bunch of methods that you can call that will give you out an acceleration. So steering algorithms operate on the premise that you pass in some parameters, it'll do some calculation, and it will give you out a type of acceleration. Now that may be a linear acceleration telling you to accelerate in a certain direction. It could be an angular acceleration telling you to rotate in a certain orientation as well. But we'll go through these. So the first one of the more probably the most simple steering behavior is seek. Seek is where you take in a seeking. So this is the case we're using sprites because they're movable objects. You take in a seeking sprite. So this is the thing that's going to seek something, and you give it a location that it's going to seek. So the demo that I had up here, the web page, you could imagine each of the light blue circles to be our entities. If I were to click in a certain location, I'm giving them a seek behavior. I'm telling them all to head to that particular location. So that's what we mean when we say we have a target position. It's where we want the seeking sprite to end up or to try to get towards. Now, we need to return an acceleration from this particular method. It's two dimensions. Our acceleration has an x and a y vector, as opposed to returning a vector 2, which would be a new object. We don't want to get into object creation costs. We pass in an empty, or basically an acceleration instance. We pass it into this particular class, and we will change the values of that by way of saying what the acceleration should be. So we do this here, so we're being efficient in terms of not creating objects when we call this method in terms of the return. So a few things we do. We have a little bit of logical checking here to see, well, is the location of the seeking sprite currently equal to the target location? In other words, have we got where we want to get to, and precisely got to it? It's very unlikely to be precisely there, but nonetheless, it's an edge case. It could happen. If that's the case, we simply say, I want you to set your velocity or your acceleration rather to 0. You don't need to go in any old direction. You're already where you want to be. So fair enough. We'll return 0 there. Else, the else is really what it does. So then it sets up initially the acceleration. So we're basing this on a vector. We go to the target position, and we work out along the X and the Y components how far we're away. So this builds initially inside our acceleration vector. We work out the vector separating the seeking entity to its target position. We work out that particular vector. So that's the complete direction and distance that we need to travel. We normalize that vector, so it gives us a unit length pointing in the direction of travel. So we at this point know the direction of travel we want to go by, and the sprite is going to have a maximum acceleration value. So that was one of the abilities, one of the variables that were built into the sprite class. So we multiply the acceleration then by the maximum acceleration that this sprite can move in. So seek assumes if you give me a target location, I will get there as fast as I possibly can. There's a more refined version on arrive, and arrive will actually work out the distance you're away from your target location and slow you down as you approach it. But seek just goes straight to it at maximum speed. So that's the seek behavior. Flee is the opposite of seek. You move away from whatever the target position is, and that could be the location of another object, as fast as you possibly can. Code's the same, except that the direction of the initial vector that we get is pointing in the opposite direction. We have arrive as our next behavior, and again, there's a video published online which will talk you through some of the different steering behaviors. I'm just going to go through them very quickly here. But arrive's a bit more fancy in that it is concerned not only with the direction of travel, but with the magnitude, how fast you're moving in that particular direction of travel. So it does something similar. It works out the direction of travel we want to go in. It has a couple of radii values that works out when you get sufficiently close to it, I should then decelerate. And we've got a split here that depending on whether or not my distance is greater than my slowdown radius, in which case it's maximum velocity. Otherwise, I want to scale the velocity, so I slow down by some controlling factor. So this says, further, the closer I get to it, the slower I want my velocity to be. I'm going to brake and decelerate. Bit of logic then at the end that basically says, okay, we know our target speed, we know what our acceleration is. We're actually going to work that out in terms of arrival acceleration, and we scale it to make sure that whatever value we calculate is not greater than what this sprite is capable of managing in terms of its maximum defined acceleration. So arrive, you give that as a location, they'll go to it, they'll slow down and they'll stop. Other ones, align. Align is a more generic one where you want to align two properties of something. So in this particular case, we're interested in aligning the orientation, the way that it's pointing. So if I have a particular sprite, I can say I want you to change your orientation to this particular value. And there's a few reasons you would actually do this. One is, and I can show you some of the code as we go through this here. If you have objects moving around the environment, you generally want them to look in the direction that they're traveling. So if I travel to the left, I turn to the left, so I look as if that's the direction I'm directly moving in. So we will very often give our entities a particular linear velocity. They're moving in a certain direction, but we will align the orientation of that sprite so that it's pointed in the direction of movement. So align's useful from that regard. You've got a smoothness value, which just determines how fast you do this here, how smoothly you move down to it, again just depending on how you want this to visually appear. The align here, the one that takes in the smoothness, is actually fairly similar to arrive. As opposed to having a certain location, we have a certain orientation. As we approach that orientation, we can slow down our rotational speed, so we gently arrive at our target orientation. Look at, I suppose, is a type of align. In that sense, we say for this particular sprint, we want to change its orientation so that it is pointing towards whatever the target position is. And we just simply work out a relative direction based on the 2 points, and we then align in that particular direction. Align with movement, again, is also another type of align method. So here we say for this particular sprite, give me its velocity. I'll work out an orientation based on its velocity, and I'll then align myself with that particular orientation. Separates, probably the final one we have inside this here. Separate says, okay, we have some sprite that's going to stay apart from something. What's it going to stay apart from? It's going to stay apart from a list of target sprites. So you can pass in a list of things that you want this to remain separate from. You've got some threshold which says that whenever I get sufficiently close to something, that's when this behavior kicks in. So I'm happy a certain distance out, but as I approach to it, this is when I start saying, oh no, I want to move apart from it. There's different ways you can trigger this. So you can have it so that when you pass over your threshold you want to sort of move apart, you may have a sort of a slight movement. Okay, I'll think about moving apart. And as you get closer and closer, the urge or the emphasis on moving apart becomes stronger and stronger. So there's different ways you can do this linearly, exponentially, in terms of how you want to scale up the need for the entity to move apart from it. And again, as an output, we get the acceleration. You can have a look at this here. It basically goes through each of the bodies. We're going to build up a separating vector because there's many of them. So there could be several things we want to move apart from. So we look where each of them are. We work out what ones were within the threshold of, and we add up all of the separating vectors, combine them together. There's a risk these things can cancel out, and that's one of the challenges with separate, is that it's a bit crude. So it just depends what's around you, and sometimes you can separate, sometimes you'll not do it particularly well. But anyway, we go through there, we work out ultimately a separate one. Again, we make sure we're not trying to exceed the types of acceleration that the sprite is capable of moving with, and that's what we return. Similar for separate down here. This one says, here's the separating sprite, here's a single sprite we want, so not a whole big list, it's just one other thing we want to stay apart from. And then we do a similar thing as we did before, but only with one object, with one separating vector being generated. So it's a more simple version. So that's a bunch of utility methods that we can use. So let's have a look just to see how this gets to be used. So if we go into our game, space demo, there's two classes here. We've got the seeker, which is the one that moves around, and we've got the turret, which is the one that was looking towards the player. So we can see how this works. So turret is a type of space entity, which is a type of sprite. It has a size, we create it. Now we're defining some values over here. Maximum acceleration, maximum velocity is 0. So basically this says this thing doesn't move, doesn't have any accelerations or velocities linearly in terms of movement. But we do give it a maximum defined angular velocity and angular acceleration. So it can rotate, and 50 degrees per second, or an acceleration of 50 degrees per second is the speed at which this thing can rotate. Has a mass, we use it for collision detection. The rest of it is quite simple, it's just the update method. Update method, we have our steering behavior, we say let's turn towards the player. So we go to our steering behaviors, we use the look at behavior, we're saying it's this particular sprite. We are looking towards, we go to our game screen and we get the player spaceship. So we're saying, okay, let's get this player spaceship, let's get its position. That's what we're looking at, that particular point. And then that will provide us with our angular acceleration. We call the update method, ultimately called the sprites update method, which will use that angular acceleration to move us in a certain direction. So we've seen the difference that, or we've seen the effects that it made here. So if we run this again, go in, there's two turrets there. So they at the minute are moving around to look. You can see that they overshot a little bit and then they sort of focus in on the player. Now, what we can do is we can tweak these values. So if I said 500 and 500, now that's that means that they can spin around really, really quite quickly, and they can rotate really, really quite quickly. So this probably will give me a degree of instability because it'll be very, very jittery and very fast moving. But we'll see. Okay, there we go. So the thing now is capable of moving a lot more quickly as I move around. But you can see what it makes visible now is more the the wobbliness of it, because it tends to overshoot as we move around, because it's high acceleration, and then can bounce back the other way. So you have a little bit more jitter. If you wanted just to make it fast overall, you could say it's able to, has strong acceleration, but maybe lower velocity. So in this particular case, it should be capable of moving a lot more quickly, changing, but it shouldn't be as jittery in terms of how it does it. So it's normally there. For the turret at the bottom, not too bad. So it's now a lot more responsive in terms of how we actually move about. So by changing the values, you can control how quickly these things rotate. Seeker then is the slightly more complex version of steering. So we had a look at this here. So it has a separate threshold. So it tries to stay apart from all of the other objects. And we're saying here, whenever you get within 75 units of another object, given the fact your overall radius is 20, so your size is 40, so 75 is where we're trying to fly apart. There, you're going to try to move apart from that to keep at least 75 units between other objects. We're going to have a few accumulators, and you'll see why later on, but they're defined here just to avoid object creation costs. But basically, for this one, there's going to be a whole bunch of competing things. There will be, we're going to try to work towards the player, we're going to try to stay apart from a bunch of other objects. And these different things we need to combine together. So an accumulator and a component of that accumulator are things that we will use. Emitters, we looked at in particle effects. So over here we define maximum acceleration velocity. So it can accelerate at this, can move at that, 50 units per second. Has 150 and 300, so it can be able to rotate quite quickly. Rest of the stuff don't worry about there. Update is where the steering behaviors come in. So there's a few things that we're doing here. One, we are seeking towards the player. So we're using the seek behavior. We're saying that this particular seeker should head towards the player's position. And that gives us our sort of default seeking acceleration. Okay, good. Then we want to separate as well. So we're trying to head towards the player. We don't want to crash into the player. We also want to stay apart from the player. So we're going to use the separate behavior. We're saying that this entity wants to remain separated from the player's spaceship. Give it a certain threshold, it's linear decay, and this is the output. So the output here, we will have a value being returned from here that tells us what accelerative value we have. It could be 0, it could be a value that takes us away from the player spaceship. And we initially say to our accumulator, because this is the first time we've used it in this update, we're going to set it to be whatever that value was calculated to be. So this line, our accumulator, contains an acceleration, potentially 0, if we need to move apart from the player ship. Beyond that, we also need to say separate from all of the other objects, the other seekers, the turrets, the asteroids. So I'm going to call separate again. This time it's also for this object. I'm going to my demo and I'm saying give me all of the entities. Now all of the entities are all of the seekers, the turrets, and the asteroids. So this contains all of the other objects that we need to separate from. Same values as before, and we'll get an output from that. Now that is going to have a certain value for all of the other objects, excluding the player. We then go to our accumulator and we add. So previously we set it because it's the first time. Now we are adding to whatever we had before, or whatever component we've got from this separate behavior. So we're building this thing up. There's a test down here to see that, right, now there's two options. Either always we're going to try to head towards the player, and we might be in a position where we're not within 75 units of anything. We're not close to the player and we're not close to anything else. In that case, this accumulator is going to be 0. It's not going to. We're not going to have any separate behaviors. We're far enough away from things not to be worried about it. And if that is the case, then we just want to use our seek behavior. However, if it's not 0, and this is what we test for here, If it's not 0, it means that we are within 75 units of some other object. And we've got a choice. I'm still trying to head towards the player, and I've now got a desire to separate from something. I've got to balance these two activities. I could say I'm going to ignore one and go with the other. I could say, well, I'm going to go 50% of one and 50% of the other. There's no right or wrong to this area. It is a matter of trial and error to see what gives you the best behavior overall. For this particular implementation, it says that as soon as we have the desire to avoid something, well, we're going to keep or seek acceleration. We're going to keep 10% of it, and we're going to combine this with 90% of our avoidance acceleration. So it kind of merges the two things together. You do a little bit of seeking, but mostly your emphasis is in avoiding the collision. I could change this to 0.5 and 0.5. I would equally merge the two of them together. And it sort of has a balance between how strongly you respond to avoiding obstacles versus how strongly you're driven by getting towards the player. And there's no right or wrong answer, it just depends on the game. Bit down here then, so at this point my acceleration contains my linear acceleration. However, I also want to say that I want to face in the direction that I'm moving. So the seekers, turning the direction they were going, they looked in that direction. So I'm going to align with movement for myself, and it gives me my angular acceleration. I then call eventually the sprite superclass. It'll use the acceleration, angular and linear, give me new velocities and rotations and new positions and orientations. So it does all of that. So we could change a few things in this as well. So let's just look at acceleration and velocity this time. So we could go for 300 and 500. So it's an order of magnitude faster. Actually, let's change everything to an order of magnitude faster, and we'll see what it does. So if you run this now, so our spaceships are capable of going in much more quickly. They're trying to get to the player. You can see, because the velocities are very large, they're heading towards the player. This wasn't arrive, this was seek, which means you head towards the player at full speed. So because they can move fast and they can accelerate fast, when they're going towards the player, they are moving by the time they get there. They do try to move out of the way. You can see with the speed they're going that quite often they can't do this based on it. But okay, so we've increased it, but maybe not overly usefully. If we just did want to get a bit of a, let's say, a quicker one, so I could do 300, 500. So I could change this. So let's say we went for 150. Actually, say 120. We still want to have quite strong. Oh, actually, no, the wrong way around. Velocity 150. So we move 3 times faster, and we will give it a strong acceleration for how it moves around. So in this case, they rotate at the same speed. They are capable of moving a good bit faster. Actually, maybe they don't rotate fast enough. But the acceleration is such that they are not zooming off. They're able to brake and accelerate reasonably quickly. And you end up with this situation, but you probably do need to change the rotational bit. Just to highlight one of the differences then, if we didn't have this align with movement, so if I took this out and I ran that, so there I'm changing their linear position, but I'm not changing their orientation. So they always look in the same direction. They don't try to change their orientation to point in the direction at which they are traveling. So you can see by tweaking some of these values, you can get quite different behaviors coming out of the system overall. Go back to wherever we had originally. There we go. Right, so that probably covers all we want to look at in terms of steering behaviors. We'll go on and have a very brief look at collision detection now. Because quite often they do go together, but we're sort of wrapping these in the same video. Now, for games, generally speaking, yes, you do need to have some way of A, detecting, and then B, responding to a collision. So working out when a collision has happened, and then working out what do you do given that collision. And that's very common. So if you had a platform game like the one you can see on the screen, there's the platforms, so to speak, that the player is moving across. You want to be able to detect when they're touching that platform. There can be collectibles that the player then can interact with. So you need to work out when they're interacting with the collectible to trigger some behavior that's appropriate to the object they're interacting with. So collision detection and collision response are important elements. So I mean, if you go back, if you were looking at this one here, so the actual character in the sense of the animated individual, that's a complex thing. There are different bits to it. It's not a regular shape. Generally speaking, when we're thinking about collision detection, we normally assume that the things that we're testing for collision with, we've bounded them in some way. We have a simple bound that encapsulates, in a good way, the object. And we then test to see if the bounds of the object, if they overlap. Now, we do this simply because it's faster. We can pick bounds which correspond to sort of simple geometric shapes. Then it's just a bit of geometry. You can work out if one shape overlaps with another shape. That's, generally speaking, easier to do. It is an approximation of the shape, but you can have some techniques that go down to sort of pixel perfect or triangle perfect collision detection if you want to, but it can be expensive and it's unnecessary in a lot of cases. I just give you an example of some of the different types of bounding volumes. You could have a sphere or a circle in 2 dimensions encapsulating it. An axis aligned bounding box is one where the axes are always along the x and y axes. So it's a regular box, doesn't rotate. An oriented bounding box or non-axis aligned bounding box is one where the box itself can rotate. You can have slabs. You can have combinations of different primitive instances. You can have capsules, lozenges, K-dopes. There's a whole bunch of different things you can use to bound objects together down to BSP trees and so on. And it's big area itself depends on the area. 2D, 3D depends on what you want to do. For us, we're really just using axis aligned bounding boxes or bounding spheres. That's the 2 examples we have. They're the simple ones. Ultimately, if you push this all the way out in terms of having, so these are objects inside your game world. If you want them to interact with one another, so if it's characters and boxes and things like this, you normally want them to interact in a way that looks plausible. And as soon as you say that, you're getting into physics engines. And basically a physics engine is something that can detect a good level of accuracy, collisions between entities, and get them to respond in a way that looks physically plausible to us. So you have some simulation of inertia, of mass, of frictional forces, and so on. And the final thing just to say here, when we're thinking about collision detection and the notion of response, it actually does apply somewhat to rendering. When we're drawing things out, and you see example here at the top one, you can have a view frustum, which is the bit of the world that you see. Somewhere in memory, you'll have all of the different objects that are currently loaded in memory for your world. Not all of them, probably, are going to be visible at a point in time. So when we're rendering and drawing things out, we also want to work out if asking is an object visible is the same as thing of saying that does this object collide with my viewport or my camera's view frustum or whatever I have. So the analogy is the same. The action is if it does, then it's potentially drawable or visible. You actually do draw it. Right, so again, well, just a little aside, because the physics things are fascinating. I've I don't have time these days, but in the past I've written a couple of simple ones. One based on Box 2D, which is sort of one of the more famous physics simulations for sort of 2D stuff. You can see a whole bunch of online examples of it. In fact, the source code's good to get and to have a look at, even to write your own particular one. It's not a particularly accurate simulation, so it's iterative, impulse based. There are more sophisticated ways that do things in physically more plausible manners, but this is a fascinating area if you want to get into it. Anyway, let's have a look at the code that we have here just to see what we have. Right, so we're thinking about collision detection over in this particular case. There's not really a huge amount we want to look at. So inside our util class, we have a collision detector. And the collision detector is going to be the one class that we use here when we're dealing with visibility checks. In the grand scale of things, this deals with what would be defined as normal rectangles or axis-aligned bounding boxes. So they're aligned along the x and y axis, they don't rotate. Okay, so when we're thinking about a collision, there's actually different ways you can think about this. In some cases, you just simply need to know, do they collide, yes or no? And if we were, for example, making if it was a health pack that we're picking up, as long as we touch it in any way or any form, we're happy with it, we'll trigger some action. Likewise, if it's something to work out if it's visible on the screen, if any bit of it's visible, doesn't matter which bit, we'll draw the thing out. Sometimes, so for example in a platform game, it does actually matter to know how two things have come together. In other words, do you have a collision on the left side, the right side, the top or the bottom? Because that can make a difference. In some platform games, you're allowed to actually jump up through a platform. So there, if you've got a collision on the bottom of the platform, you wouldn't be taking any action. But if you have a collision on the top of the platform, then you would be taking an action. So sometimes the information that you need is more than just a yes, no. It's give me a bit more information about the collision. And even here, when we say the collision type, you can have no collision type or top, bottom, left or right. So it assumes a rectangular bound. It doesn't get down to precise information about, well, what are the points of collision. And you might need that depending on the actual thing that you're doing. But just to go through this here, so we've got a simple method. Is there a collision? I can pass in two bounding boxes. So as a reminder here, bounding box, go to declaration, this one here. It's a simple class, x, y, half width and half height. All of our game objects have a bounding box. So you assume for this particular one here that you've got any two game objects, including sprites. You can say, what's their bounding box? I can call this method and I can work out true or false. Do they overlap? And it's simply based on their extents. So this would be a form of separating axis test, we know one is. But in essence, if any two, if they overlap on all of the four sides, it means that there's definitely one bit of them which they are overlapped on, and we can return true in that case. This is the slightly more sophisticated one, collision, determine collision type. So you pass in two boxes, and it's going to work out how, in what way are they actually in collision. Now, there's a bit of complexity to this here as well. So if I were to imagine I have two boxes, there's my first one and there's my second one, and we will give you a slightly different color for the second one. Now at this point here they are in collision, you can see that there. But if I were to ask you, how are they in collision? And let's assume that we're looking at from the point of view of the first block, so the blue block. You would say that there's a collision with the top of the blue block. And if you ask people, that's what they would probably say. Yes, it's the top of the block is in collision with the yellowish square. And when you ask people, well, how did that happen? They would probably imagine that the yellow square fell down and it hit the top of the blue one, and this is what we've detected. And that is actually the probable outcome, but it's not, strictly speaking, necessarily the right outcome. It could have been that the block was moving really, really fast from the right-hand side. So one update, next update, third update. So the reality is that, well, it might have hit the right-hand side of it, but just because the speed it was moving, we only get to see it halfway through. So collision detection, you actually missed the point of collision. And there's an assumption though that because you're running the update loop fairly quickly, if you want to work out how two things have actually collided, you look to see what is the direction on which there is least overlap. So there's a little bit of overlap at the top of this one here. There's a lot of overlap from the bottom's point of view, a fair amount from the left's point of view, and a fair amount from the right's point of view. So the one with least amount of overlap is the top. And because you're running this fairly quickly, and because objects shouldn't be moving that much from one update to the next, it's a reasonably safe assumption then to say that whatever axis, whatever side has the least amount of overlap, that's the one you assume the collision has happened on. It's an assumption, but it actually works in most cases. So what we're going to do here, to initially say there's been no collision type, we're going to work out what side has the minimum amount of overlap. The minimum amount is the one that's just have come into collision, and that's most likely to be our side. So we go through each of the different sides. We check the top side first of all, and we work out that if we do have an overlap, what that overlap is actually. So we set it to the top initially, and we say, okay, our minimum overlap is the amount of overlap we have at the top. We'll then check the bottom side. We'll work out, first of all, do we have any overlap in this particular one? And if it's less than our minimum overlap, then we say, oh, actually, no, it's the bottom is the one that we are the most probable side, and we store minimum overlap. Do the same with the right and do the same with the left. So at the end of this here, our collision type will tell us if we have none, top, bottom, left or right, which side it was, and we actually know how much overlap by, even though we don't return that information. And the final thing that we have here is that determine and resolve collisions. So it does a little bit more. It says, okay, you give me two game objects. So we're not passing in bounds here because we're actually going to move a game object as a consequence of this. So we're not simply interested two bounds, how do they overlap? We're interested in two game objects, do they overlap? And if so, I'm going to reposition them so they don't overlap. So there we're passing in game objects. We go through similar process before we get the bounds out. We're running the same type of test as we did before. And then finally down here, we're not simply returning with the collision type, we're going to separate the objects to move them out of collision. Now, there's a question here. If we have these two particular objects, now, do we move the blue one down a bit? Do we move the yellow one up a bit? Do we move both of them a little bit to separate them apart? And again, depending upon the particular circumstance, there's going to be an answer which is more right or wrong in this particular case. This one assumes that the first object that we pass in is the object that does the moving. So if you were using this in a collision game and you had an object that was moving, the player or an AI entity, you would pass that in as your first object. It gets to move. The second object then could be the static thing like the platform. It won't get to move as a consequence of it. And that's really all it does. You can see this. So, I mean, the example of this one running is the platform demo game. So I have a range of platforms at the bottom that I can sort of walk across. There's a rectangular bounding box around the player. Let me see if I get a random creation of platforms. So each time you do it, just randomly create it. So I can jump, I can move across. So I could actually move over this way. So at this point I can't move to the left because strictly speaking the bottom of the player's rectangle is colliding with the top of the platform to this side. And as I move across here, we still have the player's rectangle just standing on top of this one. So the collisions detect it, we're moving them apart. Eventually I'll move across and the rectangles will separate and the player will fall down. So that's all that does. It's a fairly simple approach in terms of collision detection, collision resolution. You can have a look inside the platform demo just to see how it actually does this here. But we're basically updating the player, checking to see the position is here. We're going to the player. Players class then, you're working out about movement, you're working about jumping up, you update the position, and then you call the check for and resolve collisions method, which passes in the bunch of platforms. So this one here makes use of our collision detector, determine and resolve collision. So it calls that particular method, and we get out from this the type of collision that has occurred. And depending if we've hit the top, the bottom, the left, or the right, we can change the velocity. Now at the minute, anytime you have a collision, it stops the velocity. You could set this up so that if you're colliding with the top or the bottom, you keep the same velocity in terms of the X or the Y one. So it swings and roundabouts in terms of how you respond to that particular collision. But all the stuff, if you want to look at that, is in that particular class. So just to summarize things, games that you're doing, generally speaking, you do need to have some way of detecting interaction between game objects, not just simply player interaction, user input. Alongside that, whenever you detect interaction with objects, there's also some game-specific and appropriate form of reacting to it. Very often you use bounds for doing this particular setup. Simple bounds all the way up to more complex bounds. And that makes the process more straightforward. If you have simple bounds, it's generally easy to work out, do they overlap, and it can look appropriate. If you push this out all the way up to physical realism, you'll end up in the realms of physics systems and producing physically plausible simulations. And the first bit we started this lecture off was looking at steering behavior. So again, you can impart fairly simple algorithms that get nice behavior because you're constantly running them and making new decisions. So it's relatively easy to give your AI-controlled entities some ability to navigate and move around within an environment. Challenge is tweaking this so it actually looks sort of sensible and realistic overall. So hopefully, if yes, lots of fun things you can explore within your own games.